Dana, ready? Season 3.
Yeah, geez. Come all this way.
I didn't really think we'd make it past season 1.
Here we are.
All right, ready?
Let's go.
You're listening to Cool Air Hot Takes.
Welcome to Cool Air Hot Takes. We are back and better than ever for season 3. We're your hosts. My name is Charlie Jelen, along with my running mate here, Mr. Dan Gentry. And this is a show all about buildings, energy, HVAC. So if any of that is interesting to you, you are in the right place.
Thank you to everyone who's listened from seasons 1 and 2. And of course, a very warm welcome if you're a first-time listener. We're very happy to have you here, popping into the podcast.
So what we've got lined up for the episode today, first off, HVAC headlines. We're going to get you caught up on the latest news in HVAC. Our guest today, now listener, this guy has the pulse of the largest company in the world. We've got Ali Heydari, the Director of Technical Design from Nvidia. He's going to join us today. It's going to be a very, very interesting interview, and so we're going to extend it out a little bit. And then after that, we're going to go right into your stat of the day.
Gonna be a good one.
Now, Dano.
Yo.
I know you like to jump right into the hot take portion of the episode, but we actually got a good little letter from the inbox. Let me pull it up here.
All right.
Hi, Cool Air Hot Takes guys. This question is for Dan. I've been working on an air-cooled chiller design for a data center, and I keep running into one challenge: sizing the adiabatic cooling system. Now, if we stopped here, you'd be like, yes, this makes sense. People reaching out for help on sizing things. All right, I'm going to keep reading. Now, if I had a mustache like Dan's, which, let's be honest, has more surface area than some finned coils, would that reduce the need for adiabatic pre-cooling because of the natural shading and airflow optimization? Or would the sheer size of your mustache demand even more cooling just to keep everything at peak efficiency? Thanks for taking my question. Sincerely, Cool Air Hot Takes fan club member.
We love the email. I love the applause for the mustache. How would we answer that? I mean, a lot of fins per inch, maybe, if you will.
Whiskers per inch, maybe?
Whiskers per inch. You can reject more heat. I've never heard a question relate heat rejection to mustaches before, so I'm just going to give props to the writer.
Guess who it was?
I'm going to guess Grant.
Good one. Grant from Minnesota?
Yeah, Grant from Minnesota.
Tony Arango.
Okay, yep. A lot of mustache envy out there, guys. All you got to do is stick with it and be strong.
All right. What's your hot take for the episode? Season 1 or season 3?
Season 3. First hot take is season 3. So I'm excited about this one. Carburetors. The take is, we've been talking about a lot of electrification, but let's not forget carburetors are out there, something we're going to live with, and I want to give a couple examples. So all within the last week, you guys, this is actually really funny. So about a week ago, wood splitter wasn't running. So I'm like, you know what's going on? I ordered a new carburetor, essentially slapped it in, had to do a little fuel line stuff, whatever. Couple pulls, adjusted the throttle a bit, and she's running like a dream, splitting wood. So I felt like a mechanic. I was very high. I was feeling pretty good about that. So we're going to ride dirt bikes last weekend. My son's dirt bike is idling a little low. So I get in there, adjust the air and the fuel. I screwed it all up. It was like throttle dead. I was like, man, what the hell? I got kind of upset. So I, wallowed around in misery for a little bit and then went back outside and gave it a whirl, gave it a couple turns, and this baby was humming. I'm like, Mav, get out here, take her down the street. And he was running like a dream. So I'm hot on carburetors because I'm figuring out how to get my stuff running.
Okay.
What do you got?
My hot take is, maybe this isn't so hot, but engineers need some humility.
Oh, okay.
Mm-hmm. And this one hit me in the face real hard.
Oh.
I was talking to Tony Arango, same guy that sent you the mustache email, about lift versus load. We were talking about data center stuff, but why would I select a centrifugal compressor over a screw compressor? And I was like, well, a lot of it's going to come down to lift versus load and where the operating map is going to be. And one of them will be better served for that application than the other. And then I tried to explain lift versus load, and I did an awful job. It came out just didn't come out smooth.
You used to dream about lift versus load in your sleep.
I know. That's what I'm saying. You need a little humility. You got to go back to basics. You got to remember the fundamentals.
No, I
and you
love
got
it.
to brush up on those.
We've been getting a lot of asks from our department to go to offices and be like, hey, can you guys just like cover the basics? I like to say blocking and tackling.
Yeah.
Lift versus loads, big one. Starters versus drives. What's my delta T?
Yeah.
All that kind of stuff. I think our industry is getting so young with all these senior people retiring and all these younger folks are coming in, and there's a lot of education that has to be done. And a lot of this basics isn't taught in school if you're not all into HVAC. So I love it. I think that's hot.
All right. All right, listener. Up next, we got your HVAC headlines.
HVAC headlines. Your news today.
All right, listener. It's 3 o'clock in Manitowoc. Here's your headlines. Headline number 1. Legionella, just one of many HVAC risks, microbiologist says. This is from Facility Drive. If you're paying attention to HVAC news at all, you've probably seen this. There's been a handful of outbreaks of Legionella across the country. Most notably, a couple months back, there was an outbreak in New York City, and actually 4 people died from this, and dozens more got sick from it.
I didn't realize that.
Yeah.
That's crazy.
Yeah, brutal. For listeners not familiar with Legionnaire's disease, it's a type of very serious pneumonia caused by a type of bacteria called Legionella. Legionella was originally discovered from an outbreak in 1976. There was a convention of the American Legion, which is where Legionnaires comes from, and then that's where it was originally discovered. The Legionella bacteria is actually very natural. It's present all over in really low concentrations in lakes, rivers, and groundwater. Where it becomes a problem is when it's allowed to grow uncontrolled. So this usually happens in either stagnant water or warm water where the water itself is untreated. In our industry, in the HVAC space, cooling towers can be a spot where Legionella becomes a problem because you often have elevated temperatures. Cooling towers reject heat. The water temperature is sometimes slow moving, sometimes kind of stagnant depending on its operation. And then on top of that, you have condenser fans that are evaporating water, and so you get these like mist droplets that get thrown around. And if you have Legionella, that becomes a problem. But to reduce or eliminate this risk, first thing is good preventative maintenance for your cooling tower, for any of your water systems. If you need help with that, we do have resources available. We can check your water quality. We can check and make sure that you have the right preventative maintenance in place to help take care of that. Secondly, if you're looking to design something new, you can actually completely move away from water-cooled systems. There is a trade-off there around energy efficiency. Cooling towers are very, very efficient in terms of how they reject heat. And if you move away from that, you end up putting more energy into that system. So there is a trade-off there. But one thing to note, Legionnaires due to cooling towers is not common. There are millions of cooling tower systems operating all over the world that are properly taken care of and do not have a big risk to human health. Yeah. All right, headline number 2. Why prices are soaring in the country's largest grid region. Explained in 5 charts. This is from Maryland Matters. What a great, I like it.
Maryland Matters.
Nice site, Maryland Matters. We actually talked about this once before. I think it was in season 1. We were talking about the pricing dynamics on PJM. PJM oversees the grid and the electricity markets. The territory stretches from New Jersey-ish to Chicago-ish in that part of the country. Originally, we brought this up because there was a massive price spike for the PJM capacity auction. It went from about $2 billion in 2024 all the way up to $15 billion in 2025. And these are costs that are ultimately spread across to the users of electricity in that market. Now, there was some speculation at the time that this was going to be a single event, that there were going to be some measures put in place, and we were going to add a bunch of generation, and this was going to kind of go away. Well, that didn't happen. The 2026 auction closed a couple months ago, and it went up to $16 billion. So it went even higher than last year. The article cites something that's pretty simple.
I'm guessing closing down power plants and not bringing on enough new energy.
It's not location this time. It's supply and demand, just supply and demand. So there is, there's an unprecedented high in demand for electricity. There's one chart that is really kind of indicative of where we're at right now. And it shows a projection of how much future capacity they thought they needed. So in 2021, they projected out how much power they needed in 2036. We need 155 gigawatts of power. Okay. The next year in 2022, they did the same projection and they projected I need 156. So 1 more gigawatt. Okay.
Seems to be going the wrong way.
Pretty close. In 2023, they projected we need 165 gigawatts. In 2025, this year, they projected 212 gigawatts. So originally, they estimated that they thought we'd add 5 gigawatts in 15 years. Now, today, they're estimating in 10 years, we're adding 62 instead of 5. It just shows that the demand for electricity is skyrocketing. It's from data centers, it's from electrification, it's from industrial build out. All of those are increasing. Data centers, no doubt, being the biggest part of that.
That is interesting.
What can people do?
Be more efficient.
Be more efficient. Yeah, that's a big one. Get efficient. When energy costs are high, energy reduction projects pay back faster. And then second one, if you weren't interested in demand response programs in the past, check them out. It's definitely, especially if you already know you have flexible loads and you can turn things off or shift energy around. In that market, specifically in PJM, demand response is going to be more and more lucrative moving forward.
Interesting. It's good headlines.
All right. Up next, we got Ali Heydari, the Director of Technical Design at Nvidia. Don't want to miss this one. Stay tuned. Let's talk comfort, eh? Dan, what's your favorite kind of comfort?
I would say like sunny South Florida in like July.
Okay. Well, mine is the kind of comfort that doesn't make you cry when you see your utility bill.
I like that. We've just the thing. Introducing Trane's Precedent Hybrid Rooftop Dual Fuel Heat Pump. The system that's basically the HVAC equipment of having both brains and biceps.
Unfortunately, we have neither of those things. So in mild weather, it runs on electric power. When things get frigid, it flips to gas heat, giving you the best of both worlds.
So whether you're heating or cooling in a mild climate or cold climate, Trane's got you.
All right, listener, we have a true expert, and there is zero hyperbole in that statement. This man is at the forefront of his industry. He is designing some of the most critical systems that the world will be reliant on for the foreseeable future. Welcome to Cool Air Hot Takes, Mr. Ali Heydari. How are you doing today, Ali?
I'm great. Honored to be here. Privileged to have this opportunity to talk with your audience.
Well, we're going to get into the professional side of what you do, absolutely. But I'd like to give the listener a little more personal introduction. I follow you on LinkedIn. You're traveling all over the world. You're meeting with big companies. You're going to conferences. But what do you do for fun? What does Ali do for fun? What are your hobbies? Give the listener a little bit of personal intro.
Personally, I play soccer. I play soccer twice a week, and that's one of my biggest passions. I follow Liverpool. I love Liverpool for everything they do. Big Liverpool fan. So besides that, personal life, I am a beekeeper. I have multiple hives of bees, and I make a lot of honey.
Nice.
That means I make a lot of friends with that.
Love it. What position do you play for soccer?
Forward. I play forward. I try to score 3 or 4 goals, but you can imagine at my age, people have to leave aid for me to score.
Oh, that's all good. Well, that's very good. Thank you for that. So we want to start a little bit of your background. You've worked for many notable companies. Can you give us a little bit of your background and how you got to where you're at today?
I graduated from Berkeley. I'm a thermal scientist. Actually, my work on my PhD dissertation had to do with nuclear reactor cooling. I worked as a professor for 10 years of my life. I taught thermal sciences in Iran, moved to Bay Area back again as a visiting professor to Berkeley. And this was just around the .com era. And I got engaged in industry. I wanted to always explore my passion in building products and technologies outside of my classroom. And, I found ways of, being able to build industries that, based on the knowledge I had. I worked at Sun Microsystems for about 8.5 years and moved to Facebook early days, 2018, built Facebook. After that, 4 years, I built Twitter. These are all pretty much pre-IPO. Took a lot of, work getting through the companies as they try to shape, and then was pioneering the Open Compute project. Pretty much, one of the first product that was built openly from Facebook was what I designed, at least on the cooling side of it. And then Twitter after that, I moved to Baidu, a Chinese company, spent 4 years there building data center cooling technology. It was very unique opportunity, exposed me to liquid cooling. After that, I moved actually to a completely different direction. I moved to build quantum computers. So my life, I've been building everything with air cooling, 30, 40 degrees C to quantum to 4 degrees Kelvin, and moved to Nvidia in 2019. And I started looking into liquid cooling. We knew that, based on my experience, what I had done previously in industry, that air cooling will have its time, and Nvidia had produced a great opportunity to bring in widespread application of single-phase liquid cooling. So we settled with PG25. We changed basically the medium of exchange of heat, which was air, all around the world, to a unified PG25, 25% concentration of propylene glycol with water. And that choice has been the working fluid of record. And based on that, we built where we are today. We have some of the biggest synergies in the industry, moving from air cooling to liquid cooling, something that has been the plan, in build since early 40s. And we are completely moving everything to 100% liquid cooling.
Can you give our listener a reason why you would go to 25% propylene instead of pure water?
So our biggest challenges, and anybody who has any spas and pools knows, the maintenance of anything that has to do with water alone, with odd additives, is adding bacterial buildup. And so we wanted to avoid that. Corrosion is one of the biggest issues in liquid cooling. And so PG25 was a concentration that kept the conductivity and the thermal performance of water to an acceptable level, but brought in great deal of resiliency. And we've been running with PG25 pretty successfully with very little issues since about 2020, 2021.
You are the director of technical design for Nvidia. What are you responsible for in that role?
My role is developing data center cooling technology that meets Nvidia's roadmap. So since 2019, I've been working with my team, which is a great team of engineers, and we created a platform for understanding how liquid cooling can be developed in an IT data center industry, as well as where they're going to be deployed. So our work basically started with creating what we call emulators. We emulated thermally what would be a kind of a future design of any rack that has demand for high density. So we never used any silicon. Everything that was done was, built up with, this emulators, thermal test vehicles that, basically emulated the thermophysical behavior of a rack with CPUs and GPUs and everything inside of it. And so based on that, we basically were able to create our own roadmap. And we looked into what if the racks went from what used to be 40, 50 kilowatts to a couple hundred kilowatts and beyond. With having that level of ability in, creating heat in the same platform footprint of an actual CPU or GPU, and working with industry, our partners, mostly from Southeast Asia, some in the US and Europe, to create cold plates. We created the first one-of-a-kind lab. I call that lab ground zero for liquid cooling development. And so it created the first cluster of this rack. So we had multiple of racks with thermal test vehicles, highly instrumented inside and outside of a rack. We know exactly how much fluid is going through each one of the cold plates, what's temperature, everything in between. And so we were able to create the basics of what would become today a cluster or a pod of an AI factory. And so having that ability enabled us to look into the transition from air cooling to liquid cooling will take place. And actually interesting thing that we found out is that thermodynamics did not break the back of air cooling. It was geometrical limitations and volume limitations of the racks with the density required that we needed for interconnectivity and placing so many silicons next to each other with the heat sinks that were like 8U height or 6U height with fans behind them. Because, you could always get 100 kilowatts plus of air cooling with fans and heat sinks. It would be very loud, over 100 decibels potentially, very disruptive, but you could still cool. But the moment we changed that 6 to 8U height heat sink with fans behind it, with a 1U cold plate with a skyped fin, kind of surgically removing heat from silicon with the heat cold plate attached to the back of the GPU or, CPU emulators, we were able to demonstrate that, wow, there's a huge amount of ability to remove heat from this rack, and we demonstrated that, yeah, actually multiple hundreds of kilowatts of heat can be removed. And then, suddenly we started seeing that, there's actually a roadmap for us ahead of us that Nvidia has announced, multi-megawatt racks. So if you look at the Moore's Law and, how Moore's Law flattened, for years, with GPU and invention of AI, we see that take off. And we are back to the same Moore's Law sort of a pathway. And with liquid cooling, we are able to capture that.
Yeah, thanks for kind of like the transition there. It sounds like what pushed us from air cooling to liquid cooling is physical constraints.
Exactly.
How did cold plate or liquid cooling direct to chip, how did that win out over other technologies? You think submersion or two-phase? What made you guys pick direct to chip single phase?
So during the years I was at Beidou, we had data centers that was like Inner Mongolia. I mean, as far away as you can think about. And I always think about the data center has to be managed by ways that anybody, without any tools other than their fingers, without any instructions other than what they're used to with air cooling, have to be able to manage that. So I started looking at liquid cooling exactly the same way that we treat power and electricity. You never see electrons running in the power lines. You just connect with a C19, C20 plug to the back of a server, and you're safe. You're safe in operations. We thought about liquid, exact same thing. Liquid can flow inside of the pipes, and you can plug in with a QD, quick disconnect, to the servers and to the racks. And, basically you would not require any special tool for your hand except your own fingers. And the torque and the, force associated with that should be such that anybody, female or male, should be able to handle that. So the model that I had always in my mind was an air-cooled rack that's, for the last, 70 years, everybody has been so used to. Let's build something that follows the norm, that everybody anywhere in the world, Inner Mongolia or let's say downtown Manhattan, is able to operate without any special instruction. When I put myself in that position, look at it, maybe 200 or 300, pound server that has to be lifted from a tank of liquid with arm or with robotics, and having to drain that because, you have a immersion tank, it put me in an awkward position. I mean, is this something that can be deployed anywhere in the world, anytime, and can anybody without any tools deployed? It became obvious that's not going to work. That's not going to be something that, not to say that, there have been deployment of that, but you can see naturally from human behavior, from where we are so used to, any industry, anything that we work with, any generation of car that comes, pretty much follows the same trend of what used to be before. I tried to do the same thing with racks, going to megawatt racks, keeping exact same behavior that, all of us, through this industry have been used to and operate to. So that eliminated immersion very quickly. And then looking into the immersion, we actually did a study with immersion tanks, and we saw that, there's actually limitations. The roadmap, there should be a roadmap. And so we didn't see any roadmap to the future of that. And we saw a very clear roadmap in the future of direct-to-chip liquid cooling. We started with PG25 as a single phase. Luckily, in between, Department of Energy granted us a project, and we got a project for developing a two-phase application for a megawatt rack. So now I have a two-phase application with direct-to-chip pump refrigeration in a cold plate, and we also have a single phase that Nvidia is producing. So I think end-to-end we have technology very well covered. And to me, that will be basically the technology that can, save us for the near future at least, till we see what happens next.
That's really interesting. As you think about that ubiquitous kind of concept with the human element, as racks get bigger, what has to give? Because in my mind, there's kind of this back and forth, almost like a seesaw effect between temperatures for the technical loop. They want to increase so that we can get rid of mechanical cooling, but then we're packing more and more heat and we're getting denser, and then those temperatures come down. And it's almost like they go back and forth with each iteration of technology. Where is that headed?
This is a great question. That's a challenge that we are facing head on, and I would strongly recommend your audience to tune into GTCDC event. Our CEO is going to present some of the elements of AI factories and some of the releases that Nvidia has produced. And you've seen similar gigawatt scale AI factories. We call it AI factory, not data center, because it's a mission-oriented data center. It's only is built to produce tokens. Tokens is intelligence. ChatGPT, OpenAI has. That's one version of that. And that's an outcome based on the platforms that NVIDIA produced for them. Now, going inside of a data center, there's demand for higher computations as we are trying to get as close as possible and beyond capabilities of human mind. And we're producing as much, tokens that the cluster of our devices can think as fast as a human mind and as efficient as human mind. Now, with that, there is a cost of, power consumption. So that brings a challenge. We need power. We need to have enough power to, power off these data centers that can create tokens and intelligence and AI. And cooling is probably the biggest hurdle in front of, AI factory. If I have a gigawatt AI factory, if I'm spending 20% of the power to the IT for auxiliaries, majority of which is like heat rejects through the chillers and CDUs and the pumps and the CRAWs and what have you, that means that I have to put 200 megawatts reserved for a gigawatt of power allocated for IT. 200 megawatts today is bigger than most data centers that are built. So when I was building Facebook data center, they were like 50, 60 megawatts. So 200 megawatts is not something that we can ignore. If I can cut it down to 100 megawatts, that means that I have 100 megawatts of additional IT. That for a 100 kilowatt rack, that's 1,000 additional racks that I can put inside. 1,000 additional ways of producing tokens and intelligence, just in terms of the cost. If each one of those racks is multi-million, $3 to $5 million, you can think about the cost benefit of not having to lose energy, power to losses in this heat reject system, but rather produce tokens. Now, how can we do that efficiently? Of course, anything that, goes with cooler water to the chip means that we have air-cooled or water-cooled chillers, which are, vapor compression, mechanical systems. There are losses engaged with them. Anytime that we can use dry coolers and not get any mechanical cooling systems engaged, drive, heat directly from fans and pumps to ambient, that is gain. High heat loss from the racks. So we have racks that are multi-megawatts that require, let's say, a certain temperature, but at the heat reject portion of it, we have chillers and chillers that can produce lower temperature. It's much better for, reliability. It can manage a whole lot of heat removal with a smaller footprint of that, heat reject system, but there's a cost associated, and the cost is the loss of power. Now, if we increase the temperature and have dry coolers and reject heat without interfering of the mechanical systems, then we gain, tokens, but there is reliability impacts and there is functionality. Can I deploy that anywhere, anytime in the world? So we're working with industries, first figuring out what best works for gigawatt scale data centers. So we are working through build up of the blueprints of this AI factories, what we call, working with partners such as Trane, finding ways that technology, we can't get the technology of 20, 30 years ago for AI factories that are, some estimates, we may need to have 250 gigawatt of, that's tremendous amount of, I don't know where is that, but if you have 250 gigawatts of heat rejected to ambient, you can think about what type of losses we are talking about. So waste recovery is one of the biggest challenges that we are looking into. Working again with companies that are predominant in this domain. We're working with small modular reactors. We're working with on-prem power generation, fuel cells, anybody who has any ability to bring in power on site and as well produce ways that we can, recover that waste heat. And that recovered waste heat can be used in absorption chillers, that can be used for creating cooling. A lot of ways that can be, we are looking into partners, into ways that we can work with industry and be good citizen of the universe and be able to take all of us through this new revolution, the AI revolution, very smoothly, very efficiently. At the same time, be able to not harm the environment. I think that was a long answer to a short question.
That was a long answer, but I think what I picked up there is there's a trade-off between that technical loop temperature. Is if we go higher, it probably means we don't get as dense and we take up more square footage to use dry coolers, or we use chillers, shrink the footprint, cost goes up, energy goes up. So there's trade-offs on either side, and where the future goes is probably not predictable at this point.
Exactly. One of the tools that we create is called Digital Twin. Digital Twin is we have a platform, Omniverse, and through Omniverse, we create data center digital twin. Part of what we do into our digital twin buildup is looking to the impact of the total cost of ownership, the power utilization efficiency. Think about digital twin is like a realistic 3D version of an AI factory. You can do walkthrough, you can change a chiller, you can change a cooling distribution, you can change a cryo unit. You can see instantly the impact on the entire data center, including the cost, including the power utilization efficiency. All of that is part of making sure that, we use the food that we create for our own, so we create intelligence. And intelligence is helping us very effectively to accelerate all of our design works. So we use AI extensively in our work.
All right. So I got one last question for you.
Yes.
Other than Liverpool winning the Premier League, what are you most excited about?
Second time in a row.
What are you most excited about in the industry?
I see that industry they're super excited about AI. I see a great deal of synergies in companies wanting to work together. And it's not either an Nvidia problem or Intel or AMD or, this and that. It's everybody's problem. And the fact that everybody is coming together in one room, work as one team, and, truly looking into this as probably the biggest event that I can think about that has happened since Industrial Revolution is the AI revolution. And I'm really very privileged to be in this era, working with the teams that I'm working. And as much as I love Liverpool, I also love our partners.
Wow, we're very privileged to have you on today. Elliot,
Yes.
Thank you for coming on and spending some time with us. That was awesome.
Thank you. Thank you for this opportunity. All right.
We're all about the future of HVAC over here, so we want you to join us at the AHR Expo, the world's largest HVACR marketplace.
That was kind of Uncle Sam of you right there. We want you. Trane will be showing their latest innovations in heating and cooling solutions, discover cutting-edge technology, sustainable practices, and the products that are shaping the future of the industry.
Charlie, don't forget about the best part. We'll be there live at the expo. Stop in at our booth and be a part of the conversation.
We'll be diving into the latest trends and sharing hot takes on everything we see.
Whether you're an HVAC veteran or just starting out, this is the place to be. Learn, network, and be inspired. Let's connect. We can't wait to meet you.
Here comes your stat of the day. Stat of the day. Stat of the day. All right, listener, it's your stat of the day. This one's brought to you by Construction Physics. Which states lost the most power in 2024? The stat that we're looking for is number of hours per customer of power lost in 2024. Let's start with the best. Which states do you think have the most reliable power?
The most reliable.
Yeah, give me two. Give me two.
I'm going to go with Texas is a good one. And I think Atlanta, Georgia. That's a state.
Location. All right, the best. Starting with number 5, Rhode Island. They had 2.5 hours per customer of power loss in 2024. Connecticut, 2.5 as well. Arizona, 1.8. Massachusetts, 1.7. And the District of Columbia, 1.6.
I wouldn't even have District of Columbia on my radar.
Well, they're not a state, so I can't blame you there. But all right, worst. What were the worst states?
I'm going to say Washington State and Vermont.
Okay. Number 5 in terms of the worst, West Virginia, 27.2. Texas, 27.4. Florida, not a surprise there. A lot of hurricanes, a lot of storms, 29.4. Big jump to Maine. Maine is 51.7.
Hey, Maine's close to Vermont.
That is, yeah, you're right. And then the worst state in the union for the most power lost is South Carolina.
Do they have like a natural
57.8.
disaster or something? What's
57.8
That's
hours per customer in 2024.
And the best is 1.6. Why? That seems like a lot.
That's a lot of hours, but down. Wow. Get some generators going there. That's a Generac prime sales spot.
Tell you what, that stat of the day is very interesting.
All right, listener, thank you for listening to this episode of Cool Air Hot Takes. We're very happy to be back for season 3. Remember, new episodes are released every 2 weeks on Tuesdays. Leave us a comment on Spotify or YouTube or a review on Apple.
Big news, listener. We've got merch. Send us your hot takes to coolair.hottakes@trane.com. If we feature it on the show, you might find some of that merch in your mailbox. Until next time, stay cool and keep those takes hot.